Hi, students. In this lecture, I'm going to discuss problems. Let us see first one. See the question. A capacitor of capacitance C is given a charge Q at t equal to 0. It is connected to an uncharged capacitor of equal capacitance through a resistance R. Find the charge on the second capacitor as a function of time. So given two identical capacitors, one is charged, other one is uncharged. So we have to find the charge on the second one as a function of time. Okay. So this question is taken from H.C. Verma. Let us see how to start. Let's see how to first make diagram, circuit diagram. Capacitor which is already charged and second one which is uncharged and connecting through a resistor, identical capacitors. So we have to find the charge as a function of time on the second one. Let us take this is a positive and this is negative. Let us take at one instant current is I and charge on this one is Q, which we have to calculate. So when charge flows like this becomes a positive and this becomes negative. When this charge is a Q, this must be equal to Q minus Q, right? Let us take now Kirchhoff's second law. Let us take it is anti-clockwise. See what we got here, minus I into R. So moving from high potential to low potential, minus IR. Next, high potential to low potential, minus Q by C. Next, low potential to high potential, plus charge is Q minus Q upon C. That is equal to 0. Now simplify this. In this current is nothing but dq by dt. It is the rate at which the second one is now charged. Okay. Now simplify this. IR is equal to see here what we can write, Q, IR equal to Q minus 2Q upon C. Check it once. IR equal to minus Q by C minus Q by C minus 2Q by C, remaining Q by C. So IR equal to Q minus 2Q by C. Now solve this one in the place of I, dq by dt, and take this one to here, Q minus 2Q, that is equal to 1 by RC into dt. Now integrate, take limits 0 to t. When time t0, charge equal to 0, at time t, charge is Q. So which we have to calculate. Right, now see what happens here. Integration of this one, it is minus 1 by 2 ln Q minus 2Q, that is equal to T by RC. Okay. Now take limits 0 to q. See what we get. Q minus 2q upon q, that is equal to e power minus 2t by rc, right? This become, that is equal to how much? That implies 1 minus 2q by q equal to e power minus 2t by rc. Now from that q by 2, q by 2 into 1 minus e power minus 2t by rc, right? It is just taking Kirchhoff's second law, and after that remaining it is only calculation part. Okay, let us see next one. A capacitor of capacitance C is given charge Q at t equal to 0. It is connected to an ideal battery of EMF epsilon through a resistance Kepler. Find a charge on the capacitor at time t. So this question also taken from H.C. Verma. Let us see how to start. It is now capacitor which is charged, now connecting to a battery through a resistor. Resistance is R, EMF is epsilon. Initially charge given Q. Let us take at one instant charge is Q. It is at one instant charge is Q and current is I. Let us see equation now. So take it as a positive and this is a negative. Let us take it as now Kirchhoff's second law clockwise. Then we can write high potential to low potential. That is minus Q by C, right? High potential to low potential. Next, we are moving along the current flow. It is minus IR plus epsilon equal to 0. Now simplify this. It is IR equal to epsilon minus Q by C, or epsilon C minus Q by C, right? Check it once. IR equal to epsilon minus Q by C. Epsilon is epsilon C minus Q by C. In the place of phi, write it now dQ by dt. So dQ upon epsilon C minus Q, that is equal to dt by RC. Okay. Now integrate. At time t0, charge was Q. At time t, charge is Q, which we have to calculate. Remember, while discussing charging of capacitor, exactly we have taken same equation, right? And we got same finally. The only change is when t equal to 0, charge was Q. It is not 0. That is the only change. Means just a changing limit, right? T0 charge is a Q instead of 0. And remaining just a calculation. It is now minus ln epsilon C minus Q, that is equal to T by RC. Now take limits Q to Q. So it becomes now epsilon C minus Q upon epsilon C minus capital Q, that is equal to e power minus T by RC. Now simplify this. Epsilon C minus Q is equal to epsilon C minus Q into e power minus T by RC. So now Q equal to, so now Q equal to epsilon C minus epsilon C minus Q into e power minus T by RC. Now simplify this. Minus of minus plus, I can take Q outside. Q e power minus T by RC. Remaining is now this part we have taken outside. Remaining is now epsilon C into, it is 1 minus, it is epsilon C plus, right? It is a plus epsilon C into 1 minus e power minus T by RC. So this is now charge on the capacitor as a function of time. Okay. The only change is just limits. When t is 0, it is capital Q. Okay. Let us see now next problem. Let's see the question carefully. Two square metal plates of side 1 meter are kept 0.01 meter apart like a parallel plate capacitor in air in such a way that one of the edges is perpendicular to an oil surface in a tank filled with an insulating oil. The plates are connected to a battery of EMF 500 volt. The plates are then lowered vertically in the oil at a speed 0.001 meter per second. Calculate current drawn from the battery during the process. Dielectric constant given 11, epsilon naught value is given. So this is asked for 6 marks in 1994. So main thing is we are lowering the plates into the oil, right? That means here capacitance is changing. Since the capacitance changes, charge on the plate also changes, right? Because you can see here when battery is connected, there is no change in potential, right? So Q equal to CB. When C changes, potential changes, right? So we have to focus now at what rate now this charge is changing. Let us see how to start it now. Let us make a diagram for the given data. So two plates placed parallel to each other, connected to one battery, which maintains EMF 500. Now they are placed initially like this, just touching the oil surface. And you can see after some time, now they are like this, dipping them into the liquid. Let us take at one instant, x length is inside. Okay. So given side length equal to for the plates, it is 1 meter, right? Given 1 meter, and separation, take it as d, which is given as 0.01 meter separation. Now see what happens. Charge on the plates equal to C into V. V is a constant, no change in that. When we are dipping them inside, capacitance will change. It is just like two capacitors. One is air capacitor, second one is oil capacitor, which are parallel. One is air capacitor and one is oil capacitor, which are parallel. That means if this is a C1 and this is now C2, then C value will be C1 plus C2. Okay. Now see what the value of C. C value epsilon naught coming to A. Total length equal to 1. This is X. So for this area will be 1 minus X into 1 epsilon naught A by D. D value 0.01 plus coming to here, it is a K into directly constant epsilon naught. This is X. So area equal to X into 1 K epsilon naught A by D 0.01. Okay. That is now capacitance. So now we have to calculate. So we are given at what rate now they are dipped inside. Velocity. Let us take small v. Velocity equal to given as now they are lowered at a rate of 0.001 meter per second. It is 0.001 meter per second. Now see, we can differentiate this. Current equal to dq by dt. So C into V value 500. I'm taking it outside. Epsilon naught, take it outside. Epsilon naught value, it is 8.85. 8.85 10 power minus 12. So taking this also outside, and D value also take it outside by D value 0.01. See what else left here. It is Kx plus 1 minus x, right? Kx plus 1 minus x derivative. It becomes k into v plus 0 minus v. See carefully. Derivative of kx, k into v. Derivative of 1, 0. Derivative of minus x, it is minus v. Check it once. V value 500, epsilon not given, and this is now 0.01. Right. Now here what we can do is V value substitute here, and K value given. K value is 11. 11 minus 1, 10. 10 V. So 500. 8.85 10 power minus 12. This is 10 power 1 to 10 power 2. K 11. 11 minus 1, 10. 10 into V value 10 power 1, 2, 3, 10 power minus 3. Okay. Now see what is the answer. 10 power minus 12. And here 10 power minus 3, 10 power minus 15, right? 10 power minus 15. Next, 10 square 2 plus 1 3, 3 plus 2 5. Okay, it is now 40. See how much we get, 8.85 into 5, 5 is 25, 40, 42, again 40, 42, 42.25, 42.25. Remaining is now 10 power. So here 2 and 2, 4, 4 and 1, 5, totally 5. This is 15, so 10 power minus 10, right? Or it is a 4.225, 10 power minus 9 ampere. That is now current. Okay. It is just a combination of two capacitors. Once you get that idea, remaining is only calculation part. See the next one. The figure shows two identical parallel plate capacitors connected to a battery with the switch S closed. The switch is now open at the free space, on the free space between the plates of capacitors is filled with dielectric of dielectric constant 3. Find the ratio of the total electrostatic energy stored in both capacitors before and after the introduction of the dielectric. Initially, what happened? Both are charged to same potential. Energy half CV square, half CV square. And once it is removed, means once you open the switch, if you connect a dielectric, here potential energy becomes K times, and this becomes 1 by K times. See carefully. So first, in both capacitors, energy will be each one half CV square plus half CV square. That is equal to CV square initial value. Coming to final value, one is still connected to battery. So its value becomes half KCV square. C becomes K times. Coming to second one, potential energy becomes 1 by K times, right? Without battery. This is what we have discussed while discussing effect of dielectric. When no battery, if you insert dielectric, potential energy becomes 1 by K times. See where change comes. K plus 1 by K into half CV square. K value given 3, 3 3 is 9, 9 plus 1 10, 10 by 3 into half CV square. This is 5 times. So it is now 5 by 3 CV square. Now ask the ratio at initial to final. Initial value and final value. Initial value CV square. Final value 5 by 3 CV square. So answer is now 3 by 5. That means mainly we have to keep in mind, like with the battery, if you insert dielectric, energy becomes K times. Without battery, if we insert dielectric, it becomes 1 by K times. If we have that point in mind, directly we can solve the question. I hope you got clarity.